Yeah, so indeed, this is a continuation of this talk about this strange functional. Well, it's a version of the Einstein-Hilbert functional, and well, actually, it should at least be relatively self-contained. So I won't use much of the results that Eveline explained last week, or at least up to a certain point. Of course, then it's I mean, the motivation was all really contained there, but hopefully I can give you an idea of what things work like without having to refer too much on last week's seminar. So the context, as always, is we have a complex manifold X. And it's dimension n. And we have an ample line bundle L over X. Okay, so we are interested in looking for constant scalar curvature Kähler matrix whose scalar form is in the first chain class of L. And so last week, Eveline introduced this functional that I'm going to write in a slightly different way, but it's essentially the same. So it's called EH, as in Einstein-Hilbert, and it's functional for a pair of smooth function on the manifold with positive values, and omega instead will be a Kähler class in the first chain class of L. So the functional will be the quotient of two terms. Starting with the bottom one because it's easier. It's something that we can call somehow a weighted volume. So we take the integral over x of f to the power minus n plus 1, integrate with respect to omega power n, and we normalize this by n over, sorry, we take the n over n plus 1 power of this. And instead for the numerator, it's a version of a weighted, well, a total weighted scalar curvature that can be written as f power minus n that multiplies the scalar curvature of omega plus n times n plus 1. And then we take the norm of the differential of the logarithm of f. Well, squared with respect to the metric omega, everything integrated by omega. Okay. So it will also be useful to refer to these two factors independently. So the first one I'm going to call the total scalar curvature, and I'm going to use a bold S. Of course, I'm not using blackboard bold, but you'll bear with me, even if this looks a bit ugly on the blackboard. And up to a dimensional constant, this is the same as the integral of the Tanaka-Webster scalar curvature that we saw last week. While the denominator is going to be called with a bold V, n power n over n plus 1. This is the total volume. Okay. Yeah, so up to a dimensional constant, this Einstein-Hilbert function is exactly the same function that Eveline was talking about. And you see in this, we don't really need to refer much about the to the bundle itself, other than for defining what omega will be. So we can just consider this as a function for a function on x and Kähler metric. Okay. Yeah, so well, the main motivations for considering this functional were explained last week, but let me recall some useful properties at least. So the first and the main property that we'll care about today is that if we have a cscK metric omega, then the point 1 omega is a critical point for the Einstein-Hilbert functional. So this is what we'll be mostly interested in. And sorry? Oh. Yes. So indeed, if f is 1, this of course will just be, well, okay. Actually, yeah. It's only saying something about the variations in the f direction. But but actually, this is a good point. Maybe I should write this explicitly. So if I take f to be 1 or indeed any constant, then this volume is just the volume of L to the power n over n plus 1, while on the numerator we just have the average, the integral of the scalar curvature, which we know doesn't really depend on omega. So yeah, that's also something that we will use actually. And okay, so the second thing is that a partial converse holds. So at least when we don't have automorphisms. So let's say that the reduced automorphism group of X is trivial. Then the vice versa holds. Otherwise, if we do have automorphisms, then the critical points of EH essentially correspond to Sasaki metrics of constant curvature. Okay. So the key property we will be interested in today is actually sort of behavior of EH in families actually, and its behavior in over some specific paths of Kähler metrics. But let me recall another thing that Eveline that she mentioned last week is that we have a nice relationship between the Einstein-Hilbert functional and test configurations, in particular with the Donaldson-Futaki invariant. Okay, so let's assume that we have a test configuration curly X, curly L. Let's say over, well, actually, maybe it's better to say over C or over P1. So we assume that it's a test configuration with a smooth total space. Okay, and assume also that omega in the first channel class of L is a Kähler form. Then what can we do? Well, whenever we have a test configuration, it comes with a C-star action that is linearized. So it's lifted to L. So if we fix this test configuration C-star action, since it's linearized, it comes also with the moment map with respect to omega. Okay. So for the main idea of relating this Einstein-Hilbert functional to the Donaldson-Futaki weight is that we can essentially consider the Einstein-Hilbert functional on each fiber of the test configuration. So for each, let's say, tau in C, we consider EH on the tau fiber. So let's call it X tau, L tau. And more precisely, we will compute the Einstein-Hilbert functional on on a function f that will depend on two parameters, so s and tau, and a Euler form omega tau, where, sorry, I'm having trouble managing the blackboards, where this fs tau is essentially, well, 1 minus s times this moment map, and then we have to restrict to the tau fiber, and after pulling back via the test configuration, essentially, this is to make sure that we can consider it on X itself. And similarly, omega tau will be the restriction to the tau fiber of the Euler form omega. Okay, so if we do this, then it turns out that we have a nice expansion of this Einstein-Hilbert functional in terms of the Donaldson-Futaki weight of the test configuration. So we expand this in, oh, sorry. So we can consider the Einstein-Hilbert functional for then each value of s and tau. And it turns out that the limit for tau going to 0 exists of this. And that means this expansion in S. So the first term is something that I'm going to call EH0. Then we have S times, well, I'm going to write this as the Donaldson-Futaki weight of XL. In reality, it's a positive multiple of the actual Donaldson-Futaki plus higher order terms. Okay, so what is this EH0? Well, it's nothing but this constant I've written above. Again, up to a positive multiple. And so you see that somehow the limiting behavior of our Einstein-Hilbert functional will tell us something about the Donaldson weight. Okay, so this was just a very long recap of what Eveline discussed last time. Oops. So so secretly, what's happening here is that this scalar form will come from a contact one form on the circle bundle of L. So what's actually happening is that you take n to be, well, a dual actually minus the 0 section quotiented by its radial action. So on this space now, you have a couple of S1 actions. So you have the fiber-wise action that's just generating the C star action on fibers of L. So that's called Xi. But you also have another action, right? Another action, S1, again, given by the test configuration C star action. So I'm going to call this zeta. Okay, so what happens is that this factor here essentially is something like a contact form eta evaluated on psi minus s zeta. So yeah, maybe there's a plus. No. Okay, this should be correct. Yeah, so actually this specific combination is motivated by the fact that you want to more or less couple the action on the bundle, so the multiplication on the bundle and the test configuration action. Oh. Yeah. At least if I got all my conventions correctly. Yes. Well, yes, actually, I mean, if you examine the proof of this, I think it also becomes apparent that there is some, I mean, essentially it is, it's essentially just, yes, some computations in equivariant differential geometry. Yeah. But sort of the surprising thing is that this Donaldson-Futaki weight appears, at least to me it was surprising at first. So what is my goal today is actually to use this. Yes.
Is there some form that's equivariantly closed, the whole base? Like it's 1 minus s mu plus some differential form equivariantly closed.
Well, mu is a moment map, so
certainly like s mu plus s omega is equivariantly closed. Or minus.
Yes. I'm not quite sure actually if it is equivalently close or not. Yeah, I actually don't think so, just looking at it. But I have to think about it some more. Is 1 minus... I mean, yeah, I'm afraid I don't have any motivation for that actually. So the goal would be to use this very simple, well, so the result is not simple, but the statement at least should look not too complicated. So we can use that to give a proof more or less, or well, this a new proof or a new version of this theorem by Donaldson. Now very classical. That if if there is a cscK metric, then the pair XL is K-semistable. And to do this, actually, we only need another small ingredient, a small property of the Einstein-Hilbert functional, that is its behavior along geodesics. So the general idea is that to a test configuration, we can associate a geodesic ray and then we can compare the limit for tau going to 0 of the Einstein-Hilbert functional to the Einstein-Hilbert functional on, sorry, let's say evaluated on 1, the cscK metric by using the geodesic ray. Okay, so why is this useful? Or, well, because we have two key properties of the Einstein-Hilbert functional. And it's easier to state them first, at least if I assume that I have a smooth scalar geodesic. Then the first property is that the volume functional, sorry, the total volume functional is constant on the path 1 plus s phi dot and omega phi, phi dot t, omega phi t, where phi t again is the scalar geodesic. So this is constant in t. Okay, so essentially the volume does not change if we perform this particular transformation of the potential and the scalar metric. And the second property, again assuming phi is a smooth scalar geodesic, is that the total scalar curvature functional is increasing. In t. So for t going to infinity, this increases. Okay. So these two properties actually, they can be checked by direct computation. At least in this case, where you assume that phi t is a smooth scalar geodesic, essentially all you have to do is some integration by parts, and you will find that, well, v is constant, and and s is increasing in t if s is the positive. Okay, so for positive s, this thing will be increasing. Essentially because after you do the computation, you will find that this derivative is something like n times s times the norm of the Lickner-Hurwitz operator square, or, well, up to some other constants. Okay, but again, this literally makes sense as stated only for smooth scalar geodesics. So we'll talk later what happens for general geodesics or weak geodesics.
That's the chain
wait just a second. Oh, no, sorry. Yes, you're right. We also have some, so the actual expression, that's correct. It's NS and some other constant possibly. Then we have 1 plus S pi dot to the power minus N minus 1. Maybe minus N minus 2 actually. And then the pairing of the Legendre with itself.
pointwise.
Yes, pointwise.
One line.
Sorry?
2 lines means on term.
Oh, okay. Well, I mean, I normally write L2 when I mean L2, but yeah, I make a point of having sloppy notation. But no, sorry. Of course, you're right. It's the pointwise thing. So yeah, if you check this on the paper, we wrote it in a slightly different notation. It's like the norm of this guy here, but it's essentially the same up to, again, some dimensional constant that well, it's like 2 to some power, which I now don't remember.
Sorry, 2.
Mm-hmm.
1 plus S pi 4 is. Do we need some control over the sign effect? That's increasing point.
Yeah, we need S positive and very small to make sure that this is still positive.
But don't you need some control on the sign of pi 12?
Well, it's one here gives you some positivity.
So the kind of
So you just need to be able to choose S small enough such that this thing is positive.
And is it the Legendre operator or not?
Oh, yes. Yes, it is. Thank you. Okay, so, okay, great. So how can you proceed with these two things? Well, so if now you fix a test configuration, let's say XL, that is, let's say, smooth and dominating test configuration. For your polarized manifold XL, and you're also assuming that the geodesic, that the associated geodesic segment is smooth. Then what can you do? Well, you can take the limit of the Einstein-Hilbert functional along this family. Now here I'm changing t to tau, just because when t goes to infinity, tau goes to the central fiber of the test configuration. So okay. So when you do this, well, the second property actually tells you that the volume will be constant. So we call the Einstein-Hilbert functional is the quotient of the total scalar curvature by the total volume. So here we can just write in actually the total volume of the initial metric. So we take just the total volume of 1 comma your starting metric omega 0 divided by n over n plus 1. Okay. And yeah, somewhat confusingly, omega 0 is omega on the fiber over 1. But yeah, so it's the initial metric, the cscK metric that we start with. So, well, actually, okay. Let's write omega cscK. Okay, the numerator instead, sorry, we can take the limit for tau going to 0 of the total scalar curvature of the same path. But this is increasing. So we can say that this will be, the whole fraction will be greater or equal than the Einstein-Hilbert functional evaluated at, oh, sorry. Yes. Wait. What's, no, so this should be 1 plus s times phi dot 0. Okay. And then again, your cscK metric. Okay. On the other hand, so we know that this side, so this limit, oops, this limit is has this expression here. So if we take the limit for tau going to 0 of the Einstein-Hilbert functional along our family fs tau, omega tau, then we subtract the central value of the Einstein-Hilbert functional and we divide by s. So this will be greater or equal than the value of the Einstein-Hilbert functional for f s and tau equal 1, omega cscK, minus the central value of the Einstein-Hilbert functional, again, divided by s. So taking the limit for s going to 0 plus, then this thing becomes the derivative of in s of this quantity, which is the Donaldson-Futaki invariant, again up to a positive dimensional constant. And this will be greater or equal than the derivative in s for s equals 0 of the Einstein-Hilbert functional evaluated at cscK metric. But since this is a cscK metric, then this it's a critical point for the Einstein-Hilbert function, so this thing is 0. So if this works, you will find that Donaldson-Futaki invariant is greater or equal than 0, whatever your test configuration that satisfies all these assumptions. So this seems innocent enough. However, it only works under the assumption that phi is a smooth scalar geodesic in this case. And of course, in general, we cannot really assume that. So what can we do when the geodesic is not smooth? So in general, of course, we can only hope them to be C11. So essentially, well, we cannot really apply this strategy directly, just because while the volume can be extended also to this case, the scalar curvature does not. So the volume functional can be extended to consider also pairs at omega with a much less regularity. However, for the scalar curvature part, there is no hope of doing that directly. So we need something different, right? We need some more refined way of defining the total scalar curvature. So actually, we don't directly define the scalar curvature in an extended way, but we rather focus on the scalar curvature along specific paths, which is after all more or less all we need. Oh, actually, sorry, I should have asked if there were any questions before I move on to explain what you should do to generalize this this scalar curvature functional to less regular objects. So any questions? Okay. Okay, so from now on, we fix geodesically. Yes. Okay, so we have this linearized action on the total space of a test configuration. So in this case, you again fixing some omega in the first general class of L. We consider F to be 1 minus S. Oh, sorry. Oh, in principle, it's the it's 1 minus S times the moment map with respect to omega. Now, it's in. So what turns out to be true, which is somehow what allows you to explicitly do computations, is that this is 1 plus S and then phi dot tau, where phi where this is the part of Kähler metrics you need to consider.
You're considering your geodesic wave.
Yes.
So along such waves is theta plus.
Well, yes, we have a C11 bound also in that situation, right? There's a paper by.
The derivative
of the derivative.
I
So
don't.
that's basically what Carlo went through, experiencing results for the LP ones.
Yeah, but you're right that is crucial actually to make this work at all, because if we didn't know that this was positive, it could blow up at I mean the Einstein-Hilbert could blow up at some point. Oh, sorry, my notes are doing something weird. Okay, so what was I saying? Oh yeah, we fix the basic way. IT and also FST will be 1 plus S pi dot T. Okay, so rather than trying to extend the scalar curvature to be able to compute the scalar curvature on these kind of objects, so FST and then omega phi T, what we really do is we define an action functional. So this is similar to some work of Inoue on the Perelman entropy. So also in his case, he had some trouble extending some scalar curvature weighted functional along metrics and potentials with lower regularity. So we define the action functional along our geodesic way, phi T, is a functional now of 2 variables. So I'm going to call this A of ST. And well, there's not much technology behind this. That is just an integral between 0 and t of the total scalar curvature functional of f s u omega phi u integrated with respect to u. So u is time, but just inside the integral. Okay. So the reason for doing this is that somehow if we knew that f was a killing potential, so if we knew that f was, so let's say was holomorphic in some sense, was generating holomorphic actions, sorry. Then what can we say? What could we say? Then this action functional essentially it would be something very similar to a weighted K energy. Computed only along a path, of course. And these kind of objects, these K energies, we can expect them to be convex. And well, we also expect them to have some, let's say, some nice properties. Well, first of all, we expect them to be defined, or at least definable on paths with low regularity. So actually, just to say that this is defined requires you doing some computation. And about that, just to give you an idea of what A looks like along a geodesic path, we have something S over a dimensional constant, and this is just an entropy. well, a weighted entropy. And then, of course, there's also a Ricci term. That doesn't cause too much trouble. And no, sorry. Again, this is, we should also add a weight f to the power n here. Okay. So this action function looks something like this, and you might recognize again something that looks like an entropy weighted by some power of f. And the same happens here. This is like an energy part weighted by some power of f. So just from this definition, it's relatively easy to see that A is defined along a geodesic ribbon. Sorry, I mean along a path at st omega t coming from a geodesic as before. Unfortunately, we can apply some already well-established results to show that it does have some nice properties similar to a K-energy functional. Okay, so yes.
On the difference with some point area has to be important to the potential.
Yes.
And where is that, and why is that not important to your story?
So one big difference is that this guy in principle is defined only along a path. Well, it's not really a one-dimensional thing, so it's a path in the two real variables. So this is just a function of two variables, two real variables. While the weighted K-energy is really a function on the space of Kähler matrix. It's not. It's not. In principle, it's not. Actually, to be honest, it would be slightly surprising if this was, but I'm not quite sure if I can produce an example of two paths along which this is along which you obtain two different functionals. Sorry, two different numbers, right? What is true, however, is that independently of the path, the slope of this functional at the central fiber of a test configuration is always the same and coincides with the previous expansion. So actually, let me write this precisely. So, well, a way to recover the previous strategy then so first, we need to show that the slope for t equal infinity, so let's say the asymptotic slope, and tau equals 0 in the previous notation of this functional A for fixed S is essentially what we previously called the limit for tau going to 0 of the total scalar curvature. Sorry? Oh, well, it's just that, so tau usually parameterizes a disk in the test configuration. So tau is, let's say, time flowing inwards toward the center of the disk. So tau is e to the minus t, I think, up to a factor of 2, while time t usually for geodesic rays parameterizes time going to infinity. But of course, there's I mean, it's just a reparameterization. And so the second property you need to show is that, well, your action functional is pointwise convex along the ray. And if you think about what this is saying, in particular, we should find that the second derivative in time of A is positive, but the derivative of A is the scalar curvature. So this is more or less saying that the derivative of the total scalar curvature is positive. So your total scalar curvature will be increasing morally. Okay, so if you manage to show these two things, then essentially you can recover the previous strategy quite literally. Of course, establishing these two facts is not that simple. So that is what requires 30-ish pages of computations. Anyway, I believe my time has finished, actually, since it's been a rather long day. So just let me make a couple of remarks. Yeah, about the functional depending on the paths. So the fact that the slope of this, that the asymptotic slope of the action functional does not really depend on the path is essentially, again, a consequence of the fact that that we have this kind of expansion for the behavior at the central fiber of the Einstein-Hilbert functional. And in this expansion, each term does not depend on the choice of the Taylor metric chosen on the test configuration. I mean, well, when I'm writing it like this, it's of course not apparent, but well, these two terms do not depend on the choice of metric. Actually, also the O S square terms don't depend on the choice of metric. It's just that they're slightly more cumbersome to write down. And yeah, okay. So I think I'll stop here. Thank you. Well, we don't really have a good characterizations of, well, yes, of when the, well, sorry, of course, I should have written something like greater or equal here and there. And we don't really have a good characterization of the equal zero cases, which, I mean, you would expect that they should correspond to, let's say, trivial Kähler geodesics, right? The one generated by holomorphisms, but I'm sure it's hidden somewhere in the calculations we've already made, but I can't quite put my finger on it. Yeah. But I mean, yes, it's actually quite natural to expect that the strategy can be improved to getting stability proper.
But it's true for a single geodesics.
Yes. Mhm. Mm. Mm. So I'm not quite sure if I can relate this to variations of GAT. What we do have is, I mean, we have a global formula for this. So here I've written as this zeroth term plus s times Donaldson-Futaki plus higher order terms, but actually the expression that we get is much more intrinsic somehow. It's not really, so the strategy of calculation does not really give you this expansion here. This is just let's say an accessory that I've chosen to present the topic. However, what we get is, well, maybe I can give you a slightly more precise idea of what the formula is like. And so I believe there will be an intersection formula interpretation of this. So sorry, I'm just doing it for the scalar curvature. Essentially, you get the first two terms that are proportional. So I'm going to write alpha for some proportionality constant to the total scalar curvature of some contact manifold that sits above X and L, plus another term that is essentially then the total scalar curvature of some contact form that sits above not curly X and not curly L, together with their S1 action. And then the other terms, something like an integral of the Fubini study over omega, and then here's some weight, plus some other terms that look like this. Now, the key thing to see that this does not depend on the choice of, sorry, there's supposed to be a problem here. The key thing to see that this does not depend on the choice of omega is the fact that Fs is in fact a moment map for omega, essentially. So the equivariance sits inside this relation between the weight and the form that you're integrating there as. Now, this doesn't give any deep motivation, so it's not actually an answer to your question. Still, yeah, but it's something that we are also thinking about. I'm not quite sure if I properly digested it yet.
So can you use the higher order terms in the expansion?
Oh yeah. It's all explicit. I mean, well, it's not a finite expansion because there are. I mean, you have all these guys that are to the power, let's say -n-1 or something like this. So you will get essentially just the expansion of these denominators. So yeah, I'm not quite sure how to interpret them geometrically. I think actually the best geometric interpretation is at this level, at least for now. So until we understand more.
Why is it that the geodesics are the same when you're changing? Okay, sorry. Why in the story do you see?
So I think at the bottom of it, there has to be the fact that you're looking at the usual scalar curvature. Well, this is a strange way of saying that the geodesics reflect really the geometry of the space of calorimetrics. Now, you can imagine that this sort of thing comes from some global geometric considerations like moment maps, maybe. And surely to make this scalar curvatures appear, you have to then refer back to this moment map construction by Donaldson, I guess. And there the geodesics are apparent. Now, when you change weights, what's happening here secretly is that you are considering a different kind of geodesic. It's just that you don't see it from this description, but essentially you have the usual failure geodesic here. And the key property that these Fs satisfy is that F dot, sorry, it's not simple, dot is something like the F d phi dot. So it's actually a slightly different system, but so I think that the right answer is that if you look at, if you tilt your head enough, then this should look like a system of geodesics for some different geometric structure. So I'm not sure if this is a satisfactory answer, sorry.
I don't see this calculation. So F dot is phi dot dot, which is norm squared of d phi dot. But I don't see that t phi dot is the same thing as t phi. So I can't follow the numbers.
Oh yeah, well you also have to use the Kähler geodesic, right? Well, okay, sorry. So this thing will be. This is probably slightly boring for the rest of the audience. I'm sorry about that, but I think this is what you get. So you have minus s here and there, and then you find the second thing again. Well, let's compute this after we've let everyone go off.
So in the forecast, these are like
oh. I don't know actually. So I didn't think of this very, except that no, okay. Let's just say I don't know. It's safe to assume that there will be some relation. Don't know if Eveline thinks the same, but okay. Okay, so I guess everyone is free to go. Thanks.